This is Group 1. Our topic is black box testing. It's done by Benjamin Bishop, Roger Lewis, Ben Perez, Jeremy Slotzman, and Michael Smith.
Black box testing is so named because the software program, in the eyes of the tester, is like a black box. In other words, the tester does not see inside the program. Also known as behavioral testing, black box testing is a software testing method in which the internal structure, design, and implementation of the item being tested is not known to the tester. So in simple terms, the tester will not be looking at the code. Black box testing is all about input and output, but not what comes between. As you can see in the diagram, the tester decides on some input, also called test cases, that is fed into the black box of the compiled program. Naturally, output is produced. This output will then be compared to the expected output defined by the tester and based on the software specifications. Although black box testing is not limited to functional tests, indeed, sometimes non-functional tests may be performed. Black box tests are usually functional. Black box testing is really all about testing to see if a program is working the way it should, while ignoring the why. One of the challenges of black box testing is the huge amount of possible test cases available. In fact, in many cases, there could be an infinite amount of possible inputs. How does the tester choose the best inputs for testing? Two similar techniques are used to aid in this situation, namely equivalence partitioning and boundary value analysis. Equivalence partitioning, as the name suggests, involves breaking up all possible inputs into separate divisions or classes. In the diagram, we have partitioned the possible inputs into three separate classes, A, B, and C. In equivalence partitioning, all values in each section can be treated similarly. In other words, we only have to test one value from each section and can assume that all other input values in that section will produce similar results. Second, we have boundary value analysis. This is similar to equivalence partitioning, but in this case, the focus is testing values at or near boundary lines of the classes. The reasoning for this strategy is that errors tend to pop up around the boundary lines.
Some of the advantages is test from a user point of view. There's no programming knowledge needed. It can be tested by an independent body. Test cases can be designed as soon as specifications are completed. When knowledge of the code base is not required, black box testing is used in integration level or system level because the black box test does not need to look into the source code, but just needs to execute the system by using input data and observing the output results. When the code base is not accessible, very often component users will not have access to the source code, and therefore black box testing is the most intuitive choice for them to test a software component. The disadvantages is only a small number of inputs can be tested. It may be redundant. Test cases are hard to design, so without clear specifications, which is the situation in many projects, test cases will be difficult to design. It has limited areas are covered. Only a selected number of test scenarios are actually performed. As a result, there is only limited coverage. Only a small number of possible inputs can be tested, and many program paths will be left untested. Let's start with the effectiveness of it. The primary aim of black box testing is to uncover errors and validate the software. Also, you can check the functional aspects, what the software does, not how it does it. And this is usually applied later in the stages of testing. This concludes our project of black box testing.